Welcome back to Maths with Mrs. J. I've already done a video where I showed you how to do the graph of y equals f dash x and y equals f double dash x from the original function. And this is when we don't know what the actual equation of the function is, we just know what the shape of the graph is. I wanted to do another one where I just focus on the first derivative, and I wanted to go into it in a little bit more detail. Mainly because this tends to be a very common exam question that comes up pretty much every year if you do maths methods or the equivalent, whatever state you happen to be in, or even what country you happen to be in. I've already ruled up my set of axes ready for our y equals f dash x underneath. You'll notice I've also ruled in some vertical lines through what I would refer to as some important points in our original function. Now, the important points that I'm talking about are, of course, our stationary points, which we can locate quite readily, any local maximum or minimum, any horizontal point of inflection, and any points of inflection. Of course, this one counts as both a stationary point and a point of inflection. Any points of inflection are also going to be important points for when we're trying to get this shape correct here. We already know, or we should know, that the gradient of a function is defined as the gradient of the tangent to the function at a point. And at a stationary point, the tangent will be horizontal, and therefore f dash x at those stationary points will be 0. I have already marked those in. I've already done step 1. That's a very important point to do. So locate any stationary points, and wherever those stationary points occur, for those x values, your f dash x will be 0. Then what you want to do is have a look at each section of the graph. By each section, I mean in between these vertical lines that I've drawn, and have a bit of a look, make a bit of a note in pencil about what is actually happening to the function. We can see here that the function y equals f of x is increasing. So the gradient will be positive there, okay? All right, if the function's going up from left to right, we know the gradient's positive. If it's going down from left to right, we know the gradient is negative. What also can we say, though, about the gradient? It's positive, but it's actually becoming less steep. So it's positive and decreasing. This section here, obviously the gradient will be negative because it's going down, the function's going down. It'll be negative and it's getting increasingly steeply negative, isn't it? Then it suddenly stops getting increasingly negative and starts increasing again. So it's negative and increasing. Lo and behold, our point of inflection of our y equals f of x will become, in this case, a local minimum of our gradient function. All right, next section. Okay, well, obviously the graph is going down, so the gradient is negative and it's becoming increasingly steeply negative, so it's negative and decreasing. Then it starts about here to increase again. So again, we're going to have negative and increasing, negative decreasing, negative increasing. We're actually going to have several turning points happening here, which we'll need to be careful to do a smooth curve of when we draw it. Okay, this section here, the graph is increasing at an increasingly steep rate, so it's positive and increasing. It's positive but becoming less steep, and here it's negative and becoming more steep. So how are we going to draw this? What are we going to do? Definitely use a pencil, because in order to get a smooth shape, quite often you'll need to adjust a little bit here and there. This graph is particularly fiddly around this section because you'll see what's happening is it's easy to do positive and decreasing to here. and then it's negative and decreasing and negative and increasing, but then it's got to be negative and decreasing back again. So what we're actually going to have to do is something like this. Now, we don't know quite how far down to go for our local minima, but we do know that momentarily we've got nothing happening to that gradient. It's momentarily a stationary point, all right? So it's stopped decreasing and about to start increasing. Stopped decreasing, about to start increasing. Okay, what's happening here? So the gradient's positive and increasing, and then positive and decreasing. So we're going to have something like this, where this is the local maximum. And again, we don't know how high necessarily to draw it, but as long as we have a local maximum there to show that the positive gradient has reached its maximum and then it started to decrease again. This would be a rough drawing of y equals f dash x. Is it perfect? Probably not. How would we even know whether it's going to be perfect or not? Okay, that gives you a basic shape, however, and that is roughly what you are going to get for your f dash x. Now, if you wanted to go on ahead and do f double dash x, you would just do to this function what you just did to this one. All right, so you'd go ahead and any stationary points here, the derivative will be 0 and so forth.